This video is the first in Chapter 4, which talks about distributions of random variables. In this video, we will talk about the normal distribution, which you're familiar with from this bell-shaped curve, which so often grades are posted on. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. We start by taking a closer look at the normal curve, often called the normal distribution. It's symmetric, as you can see here, about the mean. So this side is just a mirror reflection of this side. It's unimodal. It only has one peak, and it's this bell shape. The two parameters that describe a normal curve are the mean, which is the center of the curve, and it shifts the curve left or right on the axis, and the standard deviation, which talks about how far out the curve stretches. In this case, the curve stretches from -3 to 3. On this curve, the axis is rescaled, so you can see the curve stretches from 7 to 31. So this curve is much more spread out. Because our normal curves, all normal curves, are characterized by the mean and the standard deviation, we can standardize talking about different normal curves with something called z-scores. So the z-score of an observation or a number is the number of standard deviations it falls above or below the mean. Example, if an observation is 1 standard deviation above the mean, its z-score is 1. And we can calculate the z-score by putting the observation x, that number here, minus the mean divided by standard deviations. Once we have the z-score, we can use tables to solve normal probability problems, like this example here. In the main part of our video, we're going to work up to this example, but I am going to give you an overview of it. So this table here shows the mean SAT score is 1100 and the standard deviation is 200. If we select someone at random, Shannon, what is the probability that Shannon scores at least 1190 on her SAT? We can look at her score, 1190, and see that it is above the mean. In fact, it's 90 points above the mean. One standard deviation is 200 points, so half a standard deviation would be 100 points. So she's almost half a standard deviation above the mean. But we can calculate this now. The z-score is her score 1190 minus the mean 1100, and on top we get the 90. Again, that's the number of points she is above the mean, but now to convert it into standard deviations, we divide by the 200, the number of standard deviations. So now we get 90 divided by 200 is 0.45. As we said, it's nearly half a standard deviation above the mean. I've drawn now the normal curve. I have 0, that's at standard deviation is equal to 0. In other words, that's the mean. Standard deviation of 1, 2, and 3. Standard deviation 1, 2, and 3 less than the mean, or -1, -2, -3. So these are all z-scores. This -3, -2, -1, 0, 1, 2, 3. These are z-scores. In terms of points, then the 0, the mean, is 1100. 1 standard deviation away is the 1100 plus the 200, so that's 1300. 2 standard deviations away, that's 1100 plus 2 times 200, which is 400. So 1100 plus 400, that's our 1500. This is a 0 here. It looks like a 1, but it's a 0. Our 3 standard deviations away, that's 3 times 200, that's 600, plus the 1100, that'll give us 1700. We can go the other direction as well. So 1 standard deviation less than the mean will be the 1100 minus 200, so that will be 900. And actually now I have a really big pen. Over here, 2 standard deviations away, we would subtract another 200, so we'd get 700 over here. And I'm not going to write it because my pen's too big. And then another 2 standard deviations away, or 3 standard deviations, we would get 500. Shannon's score is somewhere over here, about approximately a little less than 0.5 standard deviations. So we want to know what percentage of people scored below this line. In other words, the percentage of people, that's going to represent the area under this curve here. To find the area under the curve, we're going to use this table that's standardized in terms of standard deviation. That's why we use the standardizing with z-score. So I'm over here, the z-score is 0.4, but I need a 0.45. And over here, these columns are the second decimal. So here's my 0.05. So my 0.05 with my 0.4 gives me 0.45. So I read that off, and that's 0.6736. I write that here, 0.6736, which is 67.36%. That's this area under the curve, which represents the percentage of scores that were below 1/2 or 0.45 standard deviations, which means the probability Shannon scores at least 1190. Be careful, it's not this. This shaded region is the probability that it's 1190 or lower. It's going to be this region here, which is going to be the 100% minus the 67.36. So that's going to be the 32.64%, and that's the number of scores that were above 1190. So I need that 0 here. So probability Shannon scored above 1190 is 32.64 because Shannon is randomly chosen. Probability Shannon scored below 1190 or 1190 or below is 67.36. If you followed that explanation, this section will be fairly easy for you. And if you didn't, we're going to take things a little bit slower and work up to it. So don't worry. The last topic we have is the 68, 95, 99.7 rule. It says for a normal curve, 99.7% of our data is going to be within 3 standard deviations of our mean. So in other words, when we go from a z-score of -3 to 3, the area under the curve will be 99.7%. It also says, that's the 99.7 part. The 95 says that 95% of the data will be within 2 standard deviations of the mean. So if you look at the mean, go 2 standard deviations to the left and 2 standard deviations to the right, then the area under the curve, the probability associated with the range from -2 to 2 is going to be 95%. That's the 95% part of the rule. And then 68 says that 68% of our data will fall within 1 standard deviation of the mean. In other words, when we look at the probabilities between -1 and 1, the area under the curve will be 68% of the total area under the curve. And that concludes our overview, so we're ready to start in more detail, starting with the normal curve. We start by introducing the normal curve, also called the normal distribution. It is symmetric, and by that we mean if we take this here as the center, this line is the center, we see that the left side is simply a reflection of the right side. It is unimodal, meaning there is one peak. If it had 2 peaks, something like this blue thing, it would be bimodal. If it had 3 peaks, something like this green one, and they don't have to be all the same or anything, that would just be multimodal, many peaks. But here, this normal curve is unimodal. It has 1 peak, and it has this bell shape. You can think of this like a little bell with a little ringer here. And this is a probability distribution, meaning this axis will have different values. So maybe it has the value 0, 1, 2, 3, or maybe the center of this bell curve here is 19, so it might be 19, and if we're scaling by 4 units, 19, 23, 27, 31. So at each of these points, you can look up here and see a probability that whatever x represents, maybe it's height or test scores, this would be the probability that your x has this value down below on the axis. So this would be probability x has the value 0 or something close to 0. Here you have the probability that x is something close to 2 because it's over the 2. Here on this graph you have the probability that x is something close to 23. And it's actually not exactly 0 because remember the probability that something is exactly 0 is 0 because probability is defined as area under the curve. And if you have a single point, then this rectangle has 0 for its base because a single point has 0 width, and so then your probability would be 0. But if you have just the smallest, tiniest bit of width, then you can find a probability. And what you can see about this curve is at the center, it has the highest probability of occurring. As you move away from the center on both sides symmetrically, you'll see that the probability decreases until finally it's going to be very close to zero. And that's the defining feature through the bell curve shape of the normal curve, that this middle, this mean, is at peak probability. And from there, you just kind of keep slowly, gradually decreasing your probability as you move away from the mean. The two parameters that'll completely describe a normal curve are the mean, which we designate with the mu, and the standard deviation, designated with sigma. So here is one normal curve with mean of 0. Remember, the 0 is at the center, so I put a 0 here. And standard deviation equals 1. And this here is the last topic in our overview slide, but we're going to cover it now. It's the 68, 95, 99.7 rule. And what that says is 68% of our data will be within one standard deviation of the mean. In other words, between z-scores -1 and 1. 95% of the data will be within two standard deviations of the mean. In other words, between z-scores -2 and 2. And finally, 99.7% of the data will be within three standard deviations of the mean. In other words, with z-scores between -3 and 3. So it is possible to have data with a z-score of 4 or -4 or 5 or -5, but it's extremely rare. Those are considered outliers. What that means in terms of this standard normal distribution, where the mean is 0, that means the center here is equal to 0, and standard deviation is equal to 2. According to our 68, 95, 99.7 rule, 99.7% of our data should land between -3 and 3, since our standard deviation is 1. And then here, 95% of our data should land between our -2 and 2, and finally 68% of our data should land between -1 and 1. So for the most part, the spread of our data, 99.7% of our data, is going to be spread out only by 6 units, like our -3 to 3 is only 6 units apart. We can compare this to this normal distributed curve, and here our mean is equal to 19. You can see that because that's the center of our data. And our standard deviation is equal to 4. And we're given this, and we can also see this because now 3 standard deviations away, that'll be 19 plus 3 times 4 is 12, which will give us 31. That's over here, 3 standard deviations away from 19. And the negative direction, that will be 19 minus 3 times 4, so 19 minus 12, that'll give us the 7. So here, between 3 standard deviations smaller than the mean and 3 standard deviations greater than the mean, we see that we have 24 units. So our data is much more spread out compared to here. And also our data is centered at 19 in this case. Here is a short problem or exercise. We want to write the shorthand for a normal distribution with mean equals 5 and standard deviation equals 3. So that would be that capital N, where our mean is equal to 5 and our standard deviation is equal to 3. And I'm also just going to draw this for you on this graph here. So I'm going to label it mu equals 5, standard deviation equals 3. So our mean is going to be 5. Over here, one standard deviation will add our standard deviation 3. So 5 plus 3 is 8, plus another 3 would be 11, plus another 3 is 14. Going the other direction, 5 minus 3 is 2, minus another 3 is -1, minus another 3 is -4. Let's look at this next problem. Mean is equal to -100 and standard deviation is 10. So that's mean is equal to -100, sigma is equal to 10. over here, we would draw our negative 100. If we add 10, we get negative 90. Another 10, we get negative 80. Another 10, we get negative 70. Going this way, we have negative 110, negative 120, and negative 130. So this is kind of what this graph will look like. And finally, we have mean is equal to 2, and standard deviation is equal to 9. And I'm out of graphs, so I'm not going to graph this one for you. Our next topic is standardization with z-scores, and it is this topic that allows us to use a single table for all normal curves, regardless of their mean and standard deviation. The way we can get away with using a single table for all normal distributions is the standardization with z-scores. And what we do is, instead of talking about how many units we are away from the mean, so if it's an SAT, how many points above the mean or below the mean we scored, or if we're talking about heights, how many inches we are above or below the mean, instead of talking about inches or points, what we talk about is how many standard deviations we are away from the mean. So the number of standard deviations we're away from the mean is called the z-score. So it's the number of standard deviations our observation falls above or below the mean. An example, if an observation is 1 standard deviation above the mean, its z-score is going to be 1. And we can calculate a z-score using this formula. Z is equal to our observed value x minus the mean. So this tells us how many units away we are from the mean. But then we divide by the standard deviation to tell us how many standard deviations we are away from the mean. Let's take the SAT example again, or an ACT example. So this table shows the mean and standard deviations for the total scores on the SAT and ACT. The distribution of scores are nearly normal. So here we have the mean of the SAT is 1100, the standard deviation is 200. The mean of the ACT is 21, the standard deviation is 6. If Anne scored 1300 on her SAT and Tom scored 24 on his ACT, who performed better? We will start with Anne. So she scored a 1300 minus the mean, that's 1100. So that's 200 points above the average. We see that the standard deviation is 200 points. That means she scored 1 standard deviation above average. So her z-score, z of Anne, is going to equal to 1. Tom then scored 24, and the average is 21. So he scored 3 points above average. We see the standard deviation is 6. So he scored half a standard deviation above average, or we could do the 3 divided by the standard deviations. So 3 divided by 6 is 1/2 a standard deviation above average. So Tom's z-score is now 1/2. Then on this normal curve, where we have the mean is in the center, we have our first hash mark is going to represent 1 standard deviation above the mean. Our second hash mark is 2 standard deviations above the mean. Our third hash mark is 3 standard deviations above the mean. If we go below the mean by 3 standard deviations, remember we said almost all of this area here is going to be under the curve. But that's not the point right now. We could see Tom is half a standard deviation above the mean, whereas Anne is a full standard deviation above the mean. So Anne did better because here we've kind of standardized their scores based on the mean and the standard deviation. Let's do another example. Let x be a random variable from n. Mean is equal to 3 and standard deviation is 2. So the program I use to record these videos doesn't allow me the mu and the sigma, so I just wrote out mean and standard deviation. But this is really n of this. And suppose that our measurement x is equal to 5.19. We want to find its z-score and then use the z-score to determine how many standard deviations above or below the mean x falls. For this example, I just used my formula here. So my x value is 5.19 minus our mean is equal to 3. Again, this top part is how many units you are away from the standard deviation, and then I divide by the standard deviation to see that we're 1.095. That's our z-score, which is exactly the answer to this question here. It's the number of deviations we are above the mean. That's my alarm, by the way. We have this next example. Head lengths of the brush-tail possums follow a normal distribution with mean of 92.6 millimeters and standard deviation of 3.6 millimeters. Compute the z-scores for possums with head length of 95.4 millimeters and 85.8 millimeters, which is more unusual. So here we see one head length is bigger, the other one is smaller. Computing the z-score for the 95.4, we subtract the mean, divide by standard deviation, and we get 0.78. Computing the z-score for the 85.8, we subtract the 92.6, so this will be negative, divide by the standard deviation, and we get negative 1.89. Looking at that, on this graph, we have 0.78, so something over here. And then our negative 1.89, so that's over here. This measurement here, the 1.89, the negative one, is further from the mean. So in other words, it's going to be more unusual. More people cluster around the mean. That's why there's this peak over at the mean. And then as you get further away from the mean, there's fewer and fewer people. This is the probability distribution. And now we've come to our last topic, using tables to solve normal probability problems. And what I have here is a table that's in the back of your book, one of the appendices. And the way you read this is the z-score. So the z-score can be 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1, and then 1.1. And this table only goes up to z equals 1.1. And then we also have this additional column. These columns add the second decimal place. So here we have 0.00, here we have 0.01, 0.02. Here we have 0.1. If I read over here, we're at 0.1, and then we add the 0.04, so we have 0.14. Here we have 0.1 plus 0.07, so we have 0.17. Here we have 0.6. Here we have 0.03, so we add these two together, we get 0.63. And what this number tells us, if we convert this to a percentage, so let's look at this one. This is for z equals 0.63. We have the z-score of 0.7357, which is equal to 73.57%. And this is a positive z-score. So what that tells us is for a positive z-score, and let's just say the z is over here at 0.63, this part of the shaded region represents the probabilities for all values with z-score 0.63 or less, right? The shaded region is to the left, so it's less than the 0.63. And each of these kind of is where the probability that the z-score falls within this range. So here, the shaded portion up to the point, this line that represents the z-score 0.63, is 73.57%, meaning 73.5% of the values are less than 0.63 standard deviations greater than the mean. Here we have our SAT mean and standard deviation. We say Shannon is a randomly selected SAT taker. What is the probability that Shannon scores at least 1190 on her SAT? And the first thing to note is 1190 is higher than the mean, so it's going to be over here. And the second thing to note is that she's 90 points higher. So 90 points is almost half a standard deviation, right? Since one standard deviation is 200, 100 would be half a standard deviation. So she's almost half a standard deviation above the mean. And let's look at the normal curve. So in the middle, we can write the mean, which is 1100. And then I'm going to say that mean has a z-score of 0. Remember, because the z-score talks about how far you are away from the mean. Well, you're right on the mean. You're 0 units away. One standard deviation away, so I'm going to put a z-score of 1, is our mean plus one standard deviation, or the 1100 plus 200. That will give us the 1300. 2 standard deviations away is going to give us 2 times the standard deviation, which is 400, plus 1100, so that'll give us 1500. That's a 0 there, not a 1. And then 3 standard deviations away, 3 times 200 is 600, so we add 600 to 1100 and we get 1700. So that's 3 standard deviations away. We can do the same for the other side. So 1 standard deviation less than the mean, we subtract 200 from the 1100 and we should get 900. 2 standard deviations away, we'll do 400 from the 1100 and that will give us 700. The other thing I can do is just keep subtracting 200 here. So this here will be 500. This is how we kind of standardize all our normal curves. We put it in standard units instead of these raw values. Okay, where's Shannon? She's at 1190, so she's going to be somewhere here. As we said, it's about half a standard deviation away. It's very close to 1200. But now we can formally calculate her z-score. It's the 1190 minus the mean, so we know she's 90 points away from the mean. In terms of standard deviation, then we divide by 200, and we get 0.45 standard deviations. As I said, it's very close to a half, so I put her little hash mark in blue here, close to 1/2. Using my table now, I'm going to look up the probability of the z-score of 0.45. That's Shannon's z-score. So it's 0.4, which is here, and then I need a 0.5, which is over here. So her probability of the z-score of 0.45 is 0.6736, or 67.36%. So I've written that down here. So what this picture tells me, this is her score, and it's higher than all of these other scores. This is the cumulative number or percentage of people who scored in this range from negative infinity, although they probably don't have a negative infinity score, but negative infinity all the way up to 0.45 standard deviations. This area represents how many people, what percentage scored that, which is 67.36. So she has scored higher than 67.36, or you could say 67.36 of the test takers scored below 1190. Then how many people scored higher? Well, that's 100 minus the 67.36, or 32.64% of the test takers scored above the 1190. So if you just asked, what's the probability Shannon, or anyone else really, scores above 1190 for this exam, that's 32.64%. Right, that's this area here. What's the probability Shannon, or anyone else, random person, scores below 1190? Well, that's this blue area here, the 67.36%. We have this next problem then. Edward scored a 1030 on his SAT. What is his percentile? And remember, percentile is the percentage of scores below his score, below 1130. We are going to start by calculating his z-score. So we said it was 1030. We're going to subtract the mean, and that's the number of points below, in this case, below the mean. And then we divide by the standard deviation. So he's negative 0.35 standard deviations below the mean. So 0.35 negative, so it's a third of the way. So somewhere around here. We come to our table, but you notice these probabilities are for positive z-scores, so we need to be a little bit careful. Let's look up the probability for a z-score of 0.35. So if it were positive, our 0.35, that's over here, 3 to 5, we would get 63.68%. So let's draw what that means. So remember, we're looking at this positive 0.35, which I'm going to say is something along this line. And our probability was to cover this portion here. I probably should have done this in green over here. This part in green is 63.68%. So I have that written here. The 63.68% of scores are below the z-score of positive 0.35, which means 100% minus the 63.68% are above the z-score of 0.35. This 100 minus 63.68, that's 36.32 above 0.35. And I'm going to shade this area in yellow here. Now remember, this normal curve is symmetric. So that means by symmetry, and remember this is our line of symmetry, this yellow portion is equal to this yellow portion. So in other words, 36.32% lies below z equals negative 0.35 because of symmetry. So in other words, Edward then is scored above approximately 36.32% of the test takers. So he is in the 36.32th percentile, or maybe just say the 36th percentile. Our next problem, Stuart scored a 1500. What is his percentile, and what percent of SAT test takers did better than Stuart? So we can see, actually, looking at this is pretty easy to start. We can see that he is 400 points above the mean, right? 1500 minus 1100 gives us 400. And that's exactly 2 standard deviations, because 1 standard deviation is 200, so 2 is 400. So his z-score should be 2. And in fact, we can do the calculation. The 1500 minus 1100 divided by 200 would be 2 standard deviations. Looking up z equals 2, which is not on this chart, which is unfortunate. I guess I'm going to have to tell you, I guess your book likes to use software to do this, but for a z-score equals to 2, if you looked it up on a table that went all the way to 2, which actually doesn't seem that hard to do, but anyway, you'll see that it's 0.9772. In other words, 97.72% of the test takers are below the 2. So this area under the curve from negative z-score negative infinity to 2 would be 97.72%, which means Stuart is in the 97.72 percentile, and only 100 minus 97.72, that's 2.2% of the people did better than Stuart. Our next example is based on a sample of 100 men. The heights of male adults in the US is nearly normal, with mean of 70 and standard deviation of 3.3. If Mike is 5'7" and Jose is 6'4", what percentile is Mike, or are Mike and Jose? First, I'm going to convert Mike and Jose into inches. So the 5 feet is 60 inches plus 7, so that's 67 inches. 6 times 12 is 72 plus 4 is 76 inches. And next we can compute their z-score. So Mike is the 67 minus the mean of 70 divided by standard deviation is negative 0.91, meaning Mike is 0.91 standard deviation shorter than the average. Jose is 76 minus the mean, 70, divided by standard deviations, 3.3. So Jose is 1.82 standard deviations taller than the mean. As with the other example, we see our chart doesn't have negative areas, but we can look at the positive. So we're going to look at positive 0.91. So again, it's kind of symmetric. It's very close to positive 1 standard deviation, but not quite. So 0.91 on our chart, I'm looking here, 0.9 is here, 0.01 is here. So we're at 81.86. So let me write that in green. So that's 81.86% of the area under the curve is below 0.91, positive 0.91 standard deviations. That means this yellow shaded portion is 100 minus 81.86%, which is equal to 18.14% is above the 0.91 standard deviations. And I guess I should write the standard deviation z equals 0.91, just to remind us. And now remember, by symmetry, this half of the graph looks like this half of the graph. So now if we use negative 0.91, this is also going to be 18.14% of the graph, which tells us that Mike is taller, here's Mike, than 18.14% of the people. So he's in the 18th percentile. Now we can calculate Jose's z-score. So we have the 76 inches minus the mean of 70 divided by standard deviation 3.3, and we get 1.82, which we can look up in our chart. So looking at the z-score of 1.82, we don't have that, right? We have 1.08, but we don't have a way of adding 0.8 to the 1. So this chart, I don't know why they made it so small, but this chart does not have the area for a z-score of 1.8. So the chart, if you had a different chart than the one in your book, you would see that 95.56% of the area is to the left of this z-score of 1.82. So that means 95.56% of the people are shorter than Jose, so Jose is in the 95th percentile, or close to the 96th percentile. Using the same height data, Eric's height is at the 40th percentile. How tall is he? So drawing a picture here, we have that somewhere below the 50th, and remember the mean is at the 50th percentile. Somewhere is 40% of the curve. So now I want to use this chart backwards. So I want to look something where the probability is at 40%. And I'm looking at this, and you know what? 1/2 is the highest, or 0.5 is the highest. There's nothing lower than 0.5. It doesn't go all the way down to 40%. But remember, that's because this chart is only for positive z-scores. So we need to look at the reflection. So let's just pretend like the line is here, but we don't really know it's between -1 and 2. But there's some line here. That means the reflection, we want this, whatever this negative z-score is, this positive z-score, to have the 40% above, which means below it is going to be the 100 minus the 40%. So we're looking for 60% on our chart now. Looking for 60%, we don't see anything exactly 60%, but over here, we see where we go from having a percentage about 59% to something just over 60%. So you can either use 0.26. Actually, that's a pretty good z-score. The other thing you could do is 2.55, sort of right in the middle. But actually, your book is going to use a z-score of 2.5. So again, symmetrically, if what leaves 40%, the z-score that leaves 40% above is z equals 2.5, that means the z-score that leaves 40% below this line here is going to be the z-score. I should have put a negative, so let me fix that. The z-score is equal to negative 0.25. And there are several ways we can summarize this. That is, it's 0.25 standard deviations below average, or negative 2.5 standard deviations away from the mean, or negative 2.5, and then we can multiply it by the standard deviations, 3.3 inches, and we get negative 0.825 inches. That is 8.25 inches below average, which means that's the mean is 70 minus 8.25, so is 69.18 inches. Once you had the z-score of negative 0.25, you could have plugged it into this formula for z-score. So negative 0.25 is the z-score for his height x minus the mean divided by standard deviation. Our next question, what is the adult male height at the 82nd percentile? So sort of drawing a picture of our normal curve, we want some z-score such that the area less than that is equal to 82%. Looking at this table, we see, we have 81.5%, somewhere over here around 0.92 will give us 82%. So now we have our z-score is 0.92, and we can plug it into our formula. The z-score is equal to x minus our mean divided by standard deviation, which means x must equal to 73.5%. 0.04. This next problem kind of combines a couple of things. So what is the probability a random adult male is between 5'9" and 6'2"? So the first thing we're going to do is convert 5'9" and 6'2" into inches. So 5 feet is 60 plus 9 is 69 inches. 6 feet is 72 plus 2 is 74 inches. We'll start by working with the 5'9", or the 69 inches. So the z-score is going to be 69 minus our mean of 70 divided by standard deviation 3.3, which is equal to negative 0.303. Remember, our tables don't have the negative numbers, so we're going to look up the z-score for 0.3, and we're going to get 0.6179. So drawing a picture, remember, now we're looking at the positive 0.3, so somewhere around 1/3, and that gives us the area of 61.79, this area here, which means the area on to the right of this z-score in yellow is 100 minus 61.79, which is 38.21%. Remember, by symmetry, so here's my negative 0.3 then, this yellow portion of the curve must be equal to what was this portion of this yellow curve. So it's going to equal to 38.21. So I've written that down for the z-score of negative 0.30. That's 100 minus our 61.79%, which is 38.21%. And this last topic, the 68, 95, 99.7 rule, we had already talked about. So we're ready to do our review. So first we talked about the normal curve, also called the normal distribution. It's a symmetric curve, it's unimodal, and it's bell-shaped. The two parameters that completely describe a normal curve are the mean and the standard deviation. And the standard deviation tells us how spread out the data is. The mean centers our data. We used z-scores to standardize our curve so that no matter what the mean and standard deviations are, we can use a common table. And the z-score tells us how far our number or our observation is from the mean in terms of standard deviation. So how many standard deviations it is above or below the mean. So an example, if an observation is 1 standard deviation above the mean, then its z-score is 1. This is the formula for z-score. Z is equal to our observation x minus the mean, mu, divided by standard deviation sigma. And we use tables to solve normal probability problems. And our example here was this table here shows the mean SAT score of 1100 and standard deviation of 200. If Shannon is selected randomly from a list of SAT takers, what's the probability that Shannon scores at least 1190 on her SAT? So what we did is we took a look at the 1190, we converted it into a z-score. So 1190 minus the mean, that's 90 points higher than the mean, divided by the 200 standard deviation. So that gives us 0.45 standard deviations above the mean. We looked up this 0.45 on our table. So 0.4, we looked up 0.4 here, and then through the columns we got to 0.05, and we got 67.36%. So in other words, here on our standard normal curve is approximately, actually it should be a little bit further over, but 0.45 standard deviations over. So z equals 0.45, and our percentage is 67.36% of our data, or our scores, are below 0.45 standard deviations above the mean. So the probability of scoring 1190 or higher, that's going to be the 100% minus the 67.36, so that's 32.64%. So probability Shannon scored above 1190 is 32.64%. Probability Shannon scored below 1190 is 67.36%. Finally, we had the 68, 95, 99.7 rule, which explains why we say the standard deviation tells us how spread out our data is. That's because 99.7% of our data is within 3 standard deviations of the mean. 95% of our data is within 2 standard deviations, and 68% of our data is within 1 standard deviation. And that's not to say you don't have data that's out here at 4 standard deviations or 5 standard deviations. It's just very rare. And those rare occurrences are called outliers. So that's it for this video. Thank you for watching.